Hello, you're welcome to our second alkene videos. In the first video, we already talked about the properties of alkenes and we looked at how alkenes are prepared. In this video, we'll look at their reactions. What reactions do alkenes undergo? We'll look at a few relevant reactions, but of course, we can't look at all reactions of alkenes as these are too many. So here I have an outline. I'll talk about oxidation of alkenes by the reagents listed. And then I'll talk about hydroboration and oxymercuriation followed by demercuriation. Then there's ozonization followed by ozonolysis. Then we also have hydration of alkenes and hydrohalogenation of alkenes. Probably after these, I'll talk about how alkenes react with chlorine in presence of water or bromine in presence of water. That's the hypohalous acids. Chlorine water, bromine water, as some other persons express it. So let's look at these reactions in turn. The first one, oxidation of alkenes. When an alkene is oxidized, what do we get? Well, for these three reagents that have been listed for oxidizing alkenes, all three of them will oxidize an alkene into a diol. A diol is a compound that has two hydroxyl groups, two alcohol groups. If you don't call it a diol, you may also call it a glycol. So glycols are also called diols. And that's what we get when alkenes are oxidized by any of these three reagents. Now, it means that if I have an alkene like this, let's say R and this C, double bond C, and then that's R, and then we have H and H. If this alkene is oxidized by any of these three reagents, what simply happens is that the double bond opens up, so we have a single bond there, so this is still H and that's H. Then with these two available spaces, we are going to get OH and OH. A compound like this is called a diol or a glycol. So this is the general representation, and on the arrow here I put O. That O stands for oxidation. But the oxidizing agents we could use to achieve this change would be any of these three. Now, for the first two, when they react with an alkene, when they oxidize an alkene, we say that they do so in a fashion called the syn fashion. So see what I mean? We can call this reaction, that's for these two now, or generally for the three of them first, this oxidation I'm talking about, we better refer to it as dihydroxylation. We say that the alkene is undergoing dihydroxylation. Why do we call it dihydroxylation? Because two hydroxyl groups have been added to the alkene. But the dihydroxylation reaction, is it substitution or addition? It's an addition reaction. Now, having heard that dihydroxylation is an addition reaction, is it syn addition or anti-addition? So one of them is anti, one of them proceeds by an anti-mechanism, and that's the last one, oxidation by peracids. But oxidation by osmium tetroxide and by potassium permanganate in alkali, called alkaline potassium permanganate, those ones will involve syn dihydroxylation. And what you are seeing on this side, what you have here as a product now, this product I've drawn, is referred to or is described as a cis diol. We call it a cis diol. First, it's a diol because of the two OH groups. Then in terms of its orientation, we say that it is in the cis orientation. But imagine me drawing something like this. So within reasonable error limits, what I'm drawing now is permitted. So this is H, and then that is OH, and this is H. So what you are seeing down here is also a diol because it has two OH groups. But this arrangement that we are looking at, this orientation we are looking at, is called the trans configuration. So this is trans diol and that one is a cis diol. So it means that when an alkene undergoes dihydroxylation, addition of two OH, by any of these reagents, you will get a diol. That's first. But the diol you are going to get, will it be cis or trans? that depends on which of these three you use. If you use any of the first two, you will get a diol that is cis. But if you use this last one, you get a diol that is trans. So while it is correct to say that dihydroxylation of an alkene, which converts an alkene into a diol, can be achieved with any of these three, it will also be important to note that for the first two, the diol you get is cis, whereas for the last one, the diol you get is trans. So what I've written here is osmium, a metal, tetraoxide. Then this one, RCO3H, we can write it as RCO2OH. We can write it as RCOOOH. Such compounds are referred to as peracids, and they are different from RCOOH. RCOOH is the general formula for alkanoic acids. So peracids have an extra oxygen compared to the alkanoic acids themselves. So that if I write HCOOH, for example, we say this is formic acid or metanoic acid. But HCOOH will be called performic acid. If you don't call it performic, you can call it permetanoic acid. So peracids are oxidizing agents, good oxidizing agents, and in their own case, when they bring about dihydroxylation of an alkene, they make us have alkenes, or they give us alkenes that are in what configuration now? Yeah, you're right if you're saying trans. So that's it for the first reaction, dihydroxylation of alkenes to give diols. The second reactions there would be hydroboration and oxymercuriation. And I've put those two reactions side by side. I've decided to discuss them together because of the similarity that they have. They have so much in common. That's why I'm deciding to look at them together. So let's say we have an alkene. Let's draw an alkene like this. R, C, this is H, double bond C, H, and then R again. This alkene is about to undergo two changes. So let's do it this way. In that upper case, it's reacting with B2H6 followed by H2O2. B2H6 is diborane, whereas H2O2 is hydrogen peroxide. So it can react with diborane and then the product gets oxidized by hydrogen peroxide, or it reacts with mercuric ethanoate or mercuric acetate, which we can write in shorthand like this, HGOAC2. If I were to write it by the normal convention, I'll write as CH3COO bracket 2, then HG. That's mercuric ethanoate, but trivially we call it mercuric acetate. So everything you are seeing in the bracket here is what I have represented as OAC2. In this case, after reaction with this, what will follow next is reduction. So look at the two reactions we are looking at. Item 2 here. Hydroboration followed by oxidation. Then oxymercuriation followed by reduction. So those are the two reactions we are considering. Now these two reactions have something in common. And what is that? Whether an alkene undergoes hydroboration or it undergoes oxymercuriation, the alkene will become an alcohol. Which means, in effect, whether hydroboration or oxymercuriation, what we are adding to the alkene is just H2O. So once H2O is added to this alkene, of course, it becomes an alcohol. However, when you use diborane followed by oxidation by hydrogen peroxide, the addition reaction will not follow Markovnikov's rule. You possibly have seen Markovnikov's rule in one of the previous videos, but just in case you have not, I would show you what Markovnikov's rule is, in that after reaction 2, I may just go straight to reaction 5 before returning to 4 and then to 3, just so that Markovnikov's rule is, you get to hear about it again. But I believe it's in one of the previous videos. So We are saying that for this one, hydroboration followed by oxidation with peroxide, the product you are going to get will be anti-Markovnikov. In other words, the product will not be as predicted by Markovnikov. Instead, it will be the opposite of what Markovnikov predicts. Whereas in this second case, it will be exactly as Markovnikov has predicted. So the product here would be the Markovnikov product. So hydroboration is anti-Markovnikov, but oxymercuriation is Markovnikov. Now, what is Markovnikov's rule? I'll state it simply here before I complete the reactions there. Markovnikov's rule is something like this. It says, if you have an alkene that is asymmetrical, look at this alkene for example. This alkene is asymmetrical. What does it mean to say that this alkene is asymmetrical? I'll tell you. If you cut along the double bond here, this way now, check the resulting right and left parts of the alkene and you'll see that they are different. In that on the right, what you have is just CH2, but on the left, you have a whole lot of atoms. We say an alkene like this is asymmetrical. But if you cut along the double bond and the two resulting halves are the same, e.g., what we have here, if I cut here now, from what we are seeing, on the right we have CHR and on the left CHR, assuming the R's are the same, then we say that this alkene is symmetrical. But this one is asymmetrical, and that's what Markovnikov is interested. Markovnikov has no business with symmetrical alkenes. Instead, Markovnikov's rule concerns alkenes that are asymmetrical. Then for reagents, if you consider a reagent like HCl and a reagent like Cl2, if Cl2 were to split, it gives you Cl and Cl. Fine, one of them can be taken to be positive and the other negative, but the fact remains that they are both chlorines. Whereas in the upper case, what we get is H and Cl, two different things. So for a reagent like HCl, we say it is asymmetrical. Whereas for a reagent like Cl2, we say it is symmetrical. Markovnikov's rule applies when you have an alkene that is asymmetrical reacting with a reagent like HCl that is also asymmetrical. So anytime asymmetrical meets asymmetrical, Markovnikov is present in the midst. Let me express it that way. So that if this guy were to react with HBr, HBr is definitely asymmetrical because H and Br are not the same. So that if this guy were to add on to this alkene, Markovnikov's rule can be stated in many ways, but I'd like to state it this way for this very situation. I'd like to say, add the H to the carbon that already has more H. To whom much has been given, more will be given. In that this carbon has two hydrogens, but that carbon has one. So by Markovnikov's rule, I am going to give this H of the HBr to this first carbon so that it becomes a CH2, whereas for the second carbon, it will be the one to receive the bromine. So that's Markovnikov's rule. It's all about giving H to the carbon that already has more H. Or you say, giving the negative part of the incoming compound to the carbon that already has less H. So based on that now, let's say we were to redraw this our alkene to look like this. This alkene is now asymmetrical because on the right you'd have CH2, but on the left you'd have CHR. It's asymmetrical, and for these two reactions, we already said that the overall effect is the addition of water. Is water asymmetrical? Yes, in that water is made up of H plus and OH minus. So since the water, which is the whole essence of this reaction, is asymmetrical, and this alkene is also asymmetrical, then we are going to have our reactions like this. In this first case, I would have R, C, single bond C, and then H, then up here H, and up there H, all right? And then this carbon that already has more hydrogen, that's where I'm going to put my hydrogen according to Markovnikov's rule. Then this carbon that has less in that it has 1, but that carbon has 2. So this carbon will be the guy to receive my OH group. So this is the alcohol that will be formed according to Markovnikov's rule. But we said that hydroboration is anti-Markovnikov. It means therefore that instead of this H to be attached to this carbon as shown and the OH on the other side, what you have now will be H here and OH there. What I have just done now is anti-Markovnikov. Why? Because according to Markovnikov, H is supposed to enter the carbon with more H. But what do we see here now? H is entering the carbon with less H. That makes the product anti-Markovnikov. But in this lower case, the product is as predicted as Markovnikov or by Markovnikov, so that we have RC and C. This is H, so that we have H, H, H down here, and then OH there. So this is according to Markovnikov's rule, but that is the opposite of Markovnikov's rule. So oxymercuriation followed by reduction is Markovnikov, whereas hydroboration followed by oxidation is anti-Markovnikov. So that's the difference between these two reactions. So let's try something down here. I would like to draw a structure here. Let's see how we name the product of this reaction. Let's say we have H, C, C, double bond C, H. H here and H there, then H and H. Now this compound is prop 1 in. If prop 1 in were to undergo hydroboration, the final product we get after the reaction with diborane and oxidation, the final product will be an alcohol, and that alcohol will be anti-Markovnikov, which means unlike according to Markovnikov's rule where H should be attached here because this guy has more hydrogen than the other one, H finds its way here for OH to stay there. That's anti-Markovnikov, and that's what hydroboration followed by oxidation with peroxide does. But in the case of oxymercuriation, H enters where Markovnikov has predicted it to enter, and that is the first carbon, so that OH enters the second carbon. But I'd like to tell you two more things before I leave these reactions. Those two things include, first, that before reaching these final products, there are intermediate products we get. For example, in the case of hydroboration, the intermediate product we get here would be R, C, H, C, this is H and this is H. Then down here I have H, and here I have B, H, and H. See that product, see that intermediate. So this is the intermediate you obtain when you carry out hydroboration before the oxidation by hydrogen peroxide, which gives you alcohol. Whereas in this lower case, oxymercuriation, when you carry out the initial reaction, what you get as intermediate is R, C, H, C, H, and H. All the things I've drawn so far are the things here, just the double bond that has become single. So that down here I have H, and then down here I have HgOAC2, like that. So this is the intermediate. So in both cases there is an intermediate. That's the first point I've tried to stress now. But usually during an exam, nobody wants to see the intermediate. We're interested in the final product. So first addition I've made to the normal discussion we had before is the presence of intermediates. Then the second and last thing I would like to tell us under this, that ends the whole item 2 of today's video, is the fact that this intermediate you get when you carry out hydroboration. You know, we said when it is oxidized by hydrogen peroxide, then you are going to get your alcohol. What if you decide to reduce it? Maybe using NaBH4, sodium borohydride. In that case, you don't get alcohol because it is oxidation with hydrogen peroxide that is supposed to convert this into your alcohol by anti-Markovnikov addition. But in this case, what you are going to get is the corresponding alkane. That means this compound becomes C, our product now, R, C, H and H, then C, H, H and H. So the final product is an alkane. So summary class, hydroboration is usually followed either by oxidation or by reduction. When there's hydroboration and it's followed by oxidation, we get an alcohol, but that alcohol is usually the anti-Markovnikov alcohol. Then when hydroboration is followed by reduction, we don't get an alcohol, instead we get an alkane. Then for oxymercuriation followed by demercuriation, that one gives us an alcohol exactly as predicted by Markovnikov's rule. So without wasting time, let's look at items 4 and 5. We'll look at item 5 here. Item 5 is hydrohalogenation, which means HX, which can be HBr or HCl or HI, is about to be added on to our alkene. Now, our alkene could be, okay, let's take two alkenes so that this is easy to grasp. There are two alkenes here. You pardon me, I'll leave out the hydrogens of the alkenes for time's sake. So look at these now. I've drawn two alkenes, and if we were to name them, we'd call them but 4 carbons, 2 in, and then but 1 in. One of them is symmetrical. Yeah, the upper one. If you cut along the double bond, you see the symmetry straight away. But in the lower case, you discover that it's asymmetrical. Meanwhile, in hydrohalogenation, the reagent you are adding is also asymmetrical. So that by the time I put my other reagent here, let's say it's HBr, beautiful, let's use HBr. So by the time I add HBr to the alkene, what do I expect? For the upper case, we said already, if you remember from the last example, that Markovnikov's rule only comes up when you have two guys that are asymmetrical. But in this upper case, the alkene is symmetrical, as you can see. So on the basis of that, I don't need to even know Markovnikov's rule to predict the product of this reaction. All I need to do is put the hydrogen in one position and the bromine in the other. Irrespective of how I do it, the product remains the same, 2-bromobutane. So this reaction is easy and very unlikely to be seen in an advanced level exam, because they know that irrespective of what you do, subconsciously or in full consciousness, you'd be correct. So that one is unlikely to show up. This is what you are likely to see, because in this case, if you put your bromine on the first carbon, you have 1-bromobutane, whereas if you put it on the second carbon, you have 2-bromobutane. So you'd need to know which one the predominant product will be, the main product. And I tell you, the main product is usually the Markovnikov product. So bringing Markovnikov's rule in now, we have carbon 1 and carbon 2. Carbon 1 has 2 hydrogens. Carbon 2 has 1 hydrogen. Where would H enter? That's the question. And according to Markovnikov, you give H to the carbon that already has more H. So your H is going to enter carbon 1, while your bromine enters carbon 2. So that we draw the product of that reaction like this. CH3, CH2, C, and this is bromine, and then C, and that is hydrogen. So if you see what I've done there, I have given you 2-bromobutane as the major or predominant product. So the 1-bromobutane, which is the other possibility now, we call it the minor product, but this is the major product. Now, hear these cheap questions. What if HCl had been used instead of HBr? Of course, very easy question. Instead of 2-bromobutane, we'd have obtained 2-chlorobutane. That's one. Then second, very important, what if we had hydrogen peroxide present in this reaction? Hydrogen peroxide, how would it have affected our product? Well, in the presence of a peroxide, hydrogen peroxide, Markovnikov's rule, I don't want to say becomes invalid. Instead, I'd like to put it this way. Normally, in the absence of peroxide, you normally will get two products for this reaction. The predominant one is the one we have drawn, which is 2-bromobutane. Whereas 1-bromobutane would also be formed, but will be formed as a minor product, small amounts. But when peroxide is present now, the Markovnikov product that was major in the absence of peroxide becomes minor, while the anti-Markovnikov product that was minor becomes major. So which means peroxide is able to make major product minor and minor product major. That peroxide effect I just described now only applies to hydrogen bromide. It doesn't apply to hydrogen chloride, doesn't apply to hydrogen iodide, doesn't apply to water. It applies strictly to HBr. So it means that in the presence of HBr now, as the reagent here, no peroxide, Markovnikov predominates. Peroxide is present, anti-Markovnikov predominates. But if you use HCl here, HCl, whether there's peroxide or not, the Markovnikov product predominates. So that's hydrohalogenation. We said it will give us an alkyl halide, and the alkyl halide is usually as predicted by Markovnikov. The only time the alkyl halide will be anti-Markovnikov is when your hydrogen halide is HBr in particular and peroxide is present. In that case, the addition will give you an anti-Markovnikov product as major. To end this video, let's say a word on hydration, because we've already looked at hydration in parts. If you remember hydroboration and oxymercuriation, they actually involved the addition of water. But hydration, why I decided to bring it up again, just discuss it briefly, is that there are many other ways of adding water to an alkene. So I just want to mention one point extra, it won't take much time, so that we can go on a short break, and when we return from that break, we'll focus on ozonolysis and reaction with bromine water and chlorine water. That would be the last part, and it will be very short. So for now, hydration. We already said hydration could be through hydroboration, through oxymercuriation. We've discussed those ones. But it's also possible to take an alkene, react it with water in the presence of H2SO4 so that we get an alkanol. That's our product, an alcohol. So imagine that under exam conditions, you are given this directly. Just as a simple, straightforward question. They give you this. And they put H2O by the side. You are asked to add the water. Whoever gives you this question is trying to test just one thing, and that is your knowledge of Markovnikov's rule. Because this alkene is asymmetrical, and the water molecule is also asymmetrical. So if you're ever given this, whether they put the H2SO4 there or they even put dry HCl for you, anyone they put, just know that bottom line, this is hydration, and hydration involves the addition of H plus and OH minus. So by Markovnikov now, carbon 1, carbon 2, who is worthy of receiving the H? That's carbon 1, so that the OH is on the second carbon. During live classes with my students, there's my own version of the Markovnikov's rule. I would usually say the center, the better. And each time I say the center, yes, I get a resounding the better. Because usually it's another way of seeing Markovnikov's rule. In that, when you add H and OH to this compound, it's no longer an alkene, instead it becomes an alkanol. And in alkanols, the functional group is OH. So by saying the center, the better, I'm trying to tell the students, let your functional group, which will be OH now, be as close to the center as possible. Even if not exactly at the center, let it be in. Don't keep your functional group out. And it's another way of applying Markovnikov's rule. So that if you put the OH on carbon 1 now, that means it's out. But if you put it on carbon 2, the center, the better. So for hydration, for hydrohalogenation, for reaction with chlorine water, bromine water, for most reactions where Markovnikov's rule is involved, just know that the functional group in the product would prefer to be inwards than outwards. So that's what I call the center, the better, my version of Markovnikov's rule. So that's the much we'll take in this video. In the next one, which will be the last and concluding part of alkenes, I'll talk about their reaction with hypohalous acids, bromine water, chlorine water. Then I'll talk about ozonization followed by ozonolysis. Thanks for watching. Remember to like, to share, and to subscribe. I'll see us in the next video.